Okay guys, this video is all about soaps and detergents. Investigate the structure and action of soaps and detergents. Alright, so when a fatty acid, which we know before, is a name for a very long chain carboxylic acid. So it has that. Oh, carbonyl head. Carboxylic acid head. So very long, blah, 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 blah. It reacts with a strong base, a salt, in this. So what we're talking about is acid plus a strong base gives a salt plus water. And in this case, this salt, which is the salt of this long chain carboxylic acid, is called a soap. So soap is just the salt of an acid-base reaction where the acid is a long chain fatty acid. Alright, so fatty acid plus sodium hydroxide gives soap plus water. Alright, the salt of a fatty acid just replaces the acidic hydrogen on the, so here, with a cation such as Na+. Okay, so here, excuse me, here I've drawn the molecule sodium stearate. Okay, it's a name, well, the sodium's there. The stearate is this ion here. It's made from stearic acid, which is just a long chain carboxylic acid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it's octadecanoic acid. Okay. It's a so the sodium stearate's a very common soap molecule. It contains the polar head, okay, with a long non-polar tail. So the rest of it, the carbon to carbon and carbon hydrogen bonds are non-polar. So sodium stearate is a white solid, and it's found in soaps, deodorants, rubber, and acrylic paints. Okay, so here's the molecule again. Just a little bit more detail. That polar head and the long non-polar tail. Sometimes you'll see them represented something like this, a circle with a squiggle or a zigzag, okay? Also down here, that's what it's trying to represent. So the head is a polar head. It has polar bonds in there, but no hydrogen, so it's going to attract to itself and water with dipole-dipole attractions. Okay? So quite strong forces there. Sometimes this is called the hydrophilic head or water-loving, okay? It's attracted to water because water's polar too, so it can form dipole-dipole attraction to it. Now the tail that's non-polar is sometimes called, by non-chemists, hydrophobic. Oh, why have I got head there? Hydrophobic tail. I should change that. Oh, hydrophobic tail, which I hate the word hydrophobic. It doesn't repel water. It just weakly attracts it. Okay, so there's just dispersion forces between a water molecule and this tail. Okay, there's no actual repulsion there. It's not hydrophobic. That word is used though. Okay, so when many of these come together, all the heads line up because they're strongly attracted to each other, and therefore all the tails line up in the same direction too. So they kind of self-assemble into a layer on the surface of the water too. So in the water is that head that likes to attract water, and it pushes out the tails away from the water, okay? They're not hydrophobic, they're just less attracted to the water, so they get pushed out. So this is what happens on the surface. So sometimes these molecules are called surfactants, okay? They form layers on the surface. And they can go on to form some more funny structures, okay? So once they form this surface, they can form, one of the most common ones that we'll talk about is this micelle. Okay, have a look at that. That's cut in half, but it's a spherical structure. Okay, so instead of a layer, it loops back on itself, And you can see all those heads are on the outside and all the non-polar bodies are pointing towards the middle, okay? They're pushed into the middle because the heads really like water. So they're on the outside, more closest to the water, and it's under the water. So all the tails are pushed into the middle of a sphere, okay? Called a micelle. What ends up happening is, so the heads are all attracted to the water outside. If there's any oil or non-polar molecules around, they'll get trapped in here. They'll get trapped and attracted in with the tails there. And so this micelle will form around those and form a small structure. So it will seem like oil or another insoluble molecule in water will suddenly be soluble because those oil molecules will be trapped in these micelles, okay? And that's how soaps and all that work, okay? So oil can then be dispersed in water surrounded by micelles. Okay, it's not a homogeneous solution then. It has slightly bigger chunks in it, so we call it an emulsion, okay? So soap is a thing that can make emulsion, so it's sometimes called an emulsifier as well, okay? There's a couple of other structures in the picture here. We've got a liposome and bilayer sheets. You can kind of see how they line up and how they work and what will happen. These are very important structures in biology. So liposomes carry things inside and in there, and the bilayer sheet prevents stuff from transferring through. Very important in biology. Okay, so let's just revise surface tension before we say what soaps do to surface tension. So surface tension is our observation, so the macroscopic observation of liquid droplets and their relative shapes. A droplet of a liquid with high surface tension will form a more spherical shape, like here in A. Okay, it will bead. It will form a nice sphere. Okay, with low surface tension, it won't really attract itself and it'll kind of be more smeared out. Okay, so this surface tension is a balance between the downward force of gravity and the ability for the molecules to attract each other. So liquids that have high intermolecular forces like hydrogen bonding and dipole-dipole forces like water have high surface tension, but those that just have dispersion forces have low surface tension, so stuff like oil and all that kind of thing. So surfactants, or what we're talking about here, soaps, lower the surface tension of water. What happens is, looking in this diagram, it takes up room where water molecules could be and pushes the distance between water molecules apart, okay? And that grabbing between water molecules is what gives it the high surface tension. So if you're moving those forces further apart by putting in these surfactants, you're lowering the surface tension, okay? So here I've used the same diagram to say, here is, just say, water. Here is water with soap in it. It lowers the surface tension, so you get a less beading and more spread on the surface. So we need to talk about how soaps work, okay? Love this diagram. So left to right, we've got a surface with grease on top, something very non-polar, okay? And we put in some soap molecules around. The soap molecules are going to interact with this grease layer. Notice the non-polar tails are going to be put into it because this polar head is more attracted to the water, okay? So it's going to form a layer on top with the tails in between. And what's going to happen is it will get in and between and form a kind of, trying to form a sphere around that grease over time. And it will slowly pull away parts until you get these full-blown micelles being formed, okay? So now you've got no grease on the surface, and the little grease is held in these micelles, so it seems like at our scale that the grease is dissolved, okay? And remember, it's not a solution now because it doesn't have those really tiny ions. It's now a bigger structure, so we call that an emulsion. Okay, properties and uses of different soaps and also introducing detergents. So as I said before, put it in bold here. Soaps have a carboxylate head, or like a carboxylic acid with its hydrogen swapped out. Okay, good for all-purpose cleaning. Okay, now let's introduce detergents. Detergents have the same general structure as soap. They have a polar head and a non-polar tail, but we get some variation in here, okay? And there's three main ones. So the first one that is most like soaps is called an anionic detergent, okay? So the carboxylate has a negative charge, so it's anionic. So this is also similar, okay? But notice how the head has swapped out here. Oh, I'll circle the head. It's swapped out. It's no longer a carboxylate. It's a sulfate head. Okay, so it's still a negative charge, but now we've got a sulfate. This is just one example of them. So anionic detergents, negatively charged head that are not carboxylate, because then they'd be soaps. And the most common is sulfate. Okay, so a common example of one of these molecules is called sodium lauryl sulfate. And if you read ingredients lists around the house on different products, that will be a familiar word to you. Okay, so anionic detergents are cheap to produce, and they're sometimes called harsh detergents. That term is used. Okay, so they're harsh detergents. Usually we class that on skins because they do a really good job of capturing all the oils and fats on your skin and removing them and letting all the water out and change. So you get dry hands and you get flaky skin because of these detergents you could have. So that's why they're called harsh. They do too good of a job cleaning skin. So they're used as laundry detergents, cheap dishwashing detergents, we'll get to the better ones, and general household cleaners. They're not usually used to clean skin, okay? Sometimes you might see it listed in the ingredients of some other ones, but it's usually just a tiny, tiny amount, and it's usually very low down the list, okay? But ones that have mainly these detergents are very harsh. Okay, let's contrast it with a cationic detergent. Have a look at my example head here. What have we got? We've got a positive ion. We've got like an ammonium head, okay? So cationic detergents have a positively charged head, commonly an amine. So trimethylhexadecyl ammonium chloride is an example of cationic detergent. That's what we've got here. So hexadecyl, so 16, and we've got 16 carbons long for the tail, and we've got methyl around ammonium head there. Cationic detergents, slightly more expensive to synthesize, so you're paying just a little bit more, okay? But they have these properties of bacteria don't like them, biocidal, and they also negate negative charges around them. And this is important. This is mainly what they're used for. So if negative charge builds up, these detergents will counteract that. And so they're good anti-static materials. So they're used as fabric softeners. So that harshness in fabric is static electricity usually. Hair conditioners, so you can get hair that's frizzy while you're trying to get rid of static build up there. So this will help it out. So hair conditioners, nearly saying air conditioners, but hair conditioners, fabric softeners, and they're also used for sanitizers and disinfectants because that biocidal action. Bacteria don't like them. Okay, the last category are non-ionic detergents. Okay, here's my example here. We haven't got an ion here. I've got a non-charged molecule, but we definitely still have a polar head there. Okay. So a non-ionic head, polar functional groups, such as alcohol groups. Okay, so here you can see some alcohol groups and some like ester groups in there too. These are the most expensive to synthesize, but not without, not hugely expensive. But they are brilliant dishwashing detergents as they will work in hard water. We'll talk more about hard water in a second. And they only produce a small amount of foam. So they're not going to build up so much foam that it's going to clog up the dishwasher. Okay. So they have a low polarity, but still enough to dissolve in water. Okay. So they're kind of finding what's the lowest thing that will still dissolve in water, but also good at surrounding grease. And these are the non-ionic detergents are really good for that. Okay. So they're usually in your more expensive dishwashing tablets and cleaners and stuff. Okay, they do a brilliant job. We'll talk about hard water in a second. Okay. Synthesis of soap, how you make soaps. Okay, they're made by a method of that's called saponification. Okay, it is essentially a reverse esterification reaction on a specific ester. Okay, so fats in general have this like a propane backbone, so 3 carbons long, with 3 long esters attached. See this ester group, ester group, ester group, and these R groups on the side are very long. They can all be the same. They can be slightly different, but that's called a fat or an oil, or more chemically a triglyceride. Okay, so fats are triglycerides. If we do a reaction with sodium hydroxide, we break those ester bonds. Okay, we break, and what we end up with is this molecule here, so the propane backbone with alcohol groups on it, so 1, 2, 3, propane 1, 2, 3 triol, or it's sometimes known as glycerol or glycerine. Okay, that's left over. And then what we get is those long groups. Now, instead of being an ester group on the end, they're now, look at this, they're now soaps. Okay, so we get 3 soap molecules from a triglyceride, okay, and 1 molecule of glycerol or glycerin. So that's how soaps are made. Practically, fats are mixed with sodium hydroxide, sometimes called lye, and heated until boiling. What ends up happening is the soap then precipitates at the surface, this white stuff, and is scraped off and dried. Okay, you can force the soap out of solution, and it looks like they've done it here. If you add in a heap of sodium chloride, you're adding in a heap of sodium, you're adding in more reactant, so you're getting more product, you're shifting the equilibrium to the right, and you're getting more of the soap product there. Okay, if you can recognize what film that's from, you'll recognize this process too. That's from Fight Club. Check it out. Good movie. A little bit crazy. Okay, hard water. I was talking about it before. Remember, the non-ionic detergent was good at working in hard water. Okay, let's define hard water first. So hard water is a term we use for water that has high concentrations of calcium ion and magnesium ions. Okay, these usually occur in water sources that come from under the ground, or is sometimes called bore water. So anywhere in the world where you're extracting water from the ground, it can have a lot of dissolved minerals and dissolved ions, and it can have a lot of calcium, magnesium. Okay, what that does, the calcium and magnesium, is soaps don't work properly when there's a lot of calcium and magnesium. Okay, they don't lather. What happens chemically is the calcium and magnesium salts of the fatty acid, so the calcium and magnesium replace the sodium on the fatty acid. They replace it and they produce a solid, so they precipitate out. So the soaps do not work because the calcium and magnesium turn them into a solid, and no longer a soap. Okay, so the salts of the fatty acid reach the calcium and magnesium ions and precipitate out. They cannot form surface layers of micelles then. Okay, so if they're precipitating out as a little bit of solid, they can't sit on the surface or form those micelles. They can't be a surfactant or form micelles. So the soap doesn't work in hard water. Okay, detergents are more compatible. Okay, they'll still form micelles and layers, but some of the bounding in these will be taken up by calcium and magnesium. The most ideal is the non-ionic one, and then they don't bond with the calcium and magnesium, and they still work like they're not there. Okay. Okay, one way around that you can get around this, if you've got hard water, and companies do this, they put phosphates in detergents. And what happens are phosphates first mop up the calcium 2+ and the magnesium 2+, and then the detergent, once they've gone, and the soap can do their work. Okay? All right. End of last chapter, we talked about biodiesel and its benefits and its limitations. One thing that I was talking about is how biodiesel is made, and we hadn't quite learnt the chemistry, and I saved it to this point because it's quite a similar reaction to the making of soap from a triglyceride, because biodiesel is made from fats and oils like a soap, okay? Instead of the saponification, we get an esterification reaction happening instead, okay? So here in my diagram, I've got my triglycerides the same. I've got that propane backbone, and then I've got my ester groups coming off, okay? Very long chains. If I react it with an alcohol like methanol, what ends up happening is I break it as again, so I get glycerin or glycerol, same name for the same molecule, but here instead of those ions and soaps, I get this methane on the end, closing it off. So these are long chain esters, or sometimes called fatty esters, okay? And this fatty ester is the biodiesel, okay? So we can refer to biodiesel as a fatty ester. This is the biodiesel. So 1 molecule of triglyceride, 3 molecules of methanol makes 3 molecules of biodiesel and the glycerin. So once that reaction has been done, a separation method is conducted to take away the glycerin or glycerol, and you're just left with that biodiesel that can then be put in the diesel cars and combusted. All right, you've got enough knowledge to do the worksheet now, and there's some more help in the check your understanding questions. Oh, chemical synthesis next. Okay, catch you later.